In this video, we're taking a look at what we refer to as geometric sequences. So we've talked about arithmetic sequences for a while now, which are patterns with addition and subtraction. And if you remember, we call something geometric, or say that it has a ratio, common ratio, when it's multiplying. And sometimes this can look like division as well, which we'll get to in our second problem. Okay, so for our first example, we're looking at, in this first problem, we look at dropping a ball from the bleachers, which start 16 feet high, and each time the ball bounces after that, it's only coming back up half as high as the original bounce. So you can see in our table, we've started filling this in. An initial height of 16, and so that's our start number at 0. And then half of that gives us the next height of 8. And so then we would just continue this pattern here of taking the previous height and multiplying it by half. So to find after 2 bounces, we would take 8, multiply that by a half, which to us looks like divide by 2. And so that would leave us with 4. And then to find after 3 bounces, we would take that height and multiply that by a half, which would leave us with 2. And continuing the pattern, 1, and then after not many bounces, it's getting very small. Okay. So again, if you were to just look at this middle column, which is kind of what we're working towards, to you it might look like it's divide by 2, but we can only speak in terms of multiplication. So anytime it looks like a dividing pattern, you're multiplying by 1 over that number, or the reciprocal. So just make sure to remember that from way back at the beginning of the unit. Okay, so it asks, what is the recursive rule for the sequence of heights? And remember, the recursive rule is where you tell me either a sub 0, a sub 1. In this case, they're giving us the 0 term, so let's go with that. So we'll say a sub 0 is that initial height of 16. And then to get to the next term, a sub n equals a sub n minus 1. We take the previous number, right? We take the previous number and multiply by 1/2. Okay. You can put parentheses. Some people write it like that. Some people don't use the parentheses. It's up to you. Okay, but now we're basically looking at patterns that are no longer adding, but are instead multiplying. And I always like to write my pattern at the end. I will tell you that sometimes what you'll see instead is some teachers or problems may write it out front as 1/2 and then a with the little n minus 1. So you can do it either way. That's up to you. I like to keep it as the second piece personally, but all right, so let's move on to the graph. So we haven't practiced graphing in a while, so we're going to do a scale first because that's the hard part with these. Although they were nice and they gave you exactly 16 squares going up the side here. So we're going to label our vertical axis height, okay, because that's what we're actually measuring in the problem, and it's based on number of bounces. Okay, and then like I said, they gave us exactly, if you sit here and count these, they gave us exactly 16. You can label every single square if you want to. I like labeling every other one so I don't have quite as crowded of a graph. But again, that's your call. So we're going by ones. I'm just labeling every other square to make it a little bit easier to read. Okay. And bounces. Again, I'm just going to label every other, but we're going by ones still. Okay. All right. So the first bounce started way up at the top, and at the beginning, before it bounced at all, it started at a height of 16 feet. And then at 8, so again, I'm just using our values here in the table. So we've already got our points here, x and y. So our next one will be at 1, 8. So at 1, which is right here, we're going to go up to 8 and put a dot. Then we had 2, 4, 4, 2. Oh, oops. 3, 2, my bad. 4, 1. And then by the time we got to 5, it was really small. Right? It was like at a half. All right, half a foot. And what I want you to do as best you can is take your pencil and actually connect these points. And you'll notice it's not making a straight line, but instead is making a curved line. Okay? That's why the multiplying patterns look very different than adding patterns. So it should create some sort of curved, decreasing line. Now they want us to write an explicit rule for the sequence of heights, and I'm going to assume they want us to write the a sub 0 one since they gave us 0, and that one's easier to use for plugging stuff in. So let h represent the height of the ball after each bounce, and b represent the number of bounces. So they want us to use function notation here. So instead of like a of n, which is what we've been using for arithmetic sequences, we're going to use h for height based on number of bounces. Okay. All right, so the initial height of our ball was 16 feet. And then after that, what we're really doing each time, and it might be easier to see in the table, is we're just multiplying by a half over and over and over again based on how many bounces have gone by. So what we're going to do here is we're going to put times a half, and I like to put parentheses here. You can put the little dot for multiply. But times a half, and then now that we're working with repeated multiplication, we use exponents to show this. Okay, so instead of writing 1/2 in, we're not doing that because repeated multiplication is using exponents. So this is how we represent geometric sequences explicitly, with a little exponent. So then they want us to use this to find the height after the 11th bounce. So bounce number 11. And you would definitely use your calculator for this, and you would type it in just the way it's written here. And you would plug in a little 11 after you type in the caret button. And knowing that on bounce 5 it was already at half a foot, obviously the 11th bounce is going to be really tiny. So I'm going to estimate this to be about, it's got a lot of zeros. 0.0078. We'll just leave it there. I think it's 125, but that's good enough. So not very tall at all. That would be very hard for us to actually see. So it's going to be very, very small on the 11th bounce. At this point, if you're not getting this number on your calculator, you need to notify a teacher so we can help you out with the calculator buttons. Okay, so in the second example, it's a completely different scenario. And it says a certain type of bacteria cell splits into 2 every hour. Suppose a culture of bacteria begins with 3 bacteria cells. So this is kind of counterintuitive to me, but when it says split into 2, what that's actually doing is getting larger, right? So if you have something, right, and it splits into 2, you just cut it right down the middle. Oh, well, that was not a very good example. I have something and then I cut it right down the middle. What I have now is something split into 2, so it's actually getting to larger and larger amounts, right? Because then it would be 4 pieces. I mean, you guys are in science. You know how this works. Okay, but splitting into 2 means times 2, not times a half. That's where people get turned around there. All right, so we've got 3 bacteria cells to start with. That's our initial amount. And then we're splitting it into 2, and that gives us the next amount, which is 6. So then if I have 6 cells and those split into 2, I'm going to end up with 12. If those split into 2, we then get 24, and then 48, and then, what's that going to be? 96? 96. Okay, so you can see it grows very, very quickly. So what is the recursive rule for the sequence of bacterial cells? Well, that's not a word. It starts with 3. So we're going to say, again, it's starting at 0 here, so I'm going to say a sub 0 equals 3. And then to get to the next term, we take the previous term, and what you can see we do over and over again is multiply by 2. And again, some people write it like that. Some people write the 2 out front, kind of like how we write 2x. I don't care which way you write it. They're both the same to me. Okay, but we're multiplying by 2 each time to get that next term in the sequence. So now let's see how this graph differs and maybe is also similar to our first graph. So on the y-axis, we're going to have bacteria cells. Really, it's the number of, I guess I should put number, bacterial cells. And then we have hours going along the x-axis. Now this one we do have to actually think a little bit more. I found it was actually easier to go by tens here because 5s wasn't quite enough. We didn't make it all the way up to 96 or higher. So we're just going to go by tens. I'm actually going to label every one this time because this one's harder to estimate with than when we go by ones. So, Okay, we're definitely getting up to 96. And then going across the bottom, we can just go by ones. It's not anything very exciting because we only look at the first 5 hours. So, let's take a look. For our first point, at 0 hours, we started with 3 bacteria cells. So 3 on this scale is not going to be very far from 0 if that whole entire first square represents 10. It would definitely be below halfway. Okay, and then it doubles and we get 6 bacteria cells after 1 hour. So we're just barely over the halfway mark now, but still not past the first line. And then finally at 2 hours we get to 12, which is slightly above that first line. Slowly. Then we jump to 24. So that's a pretty large, so we're going past the second line here, about halfway, a little bit less than halfway. Then it's 48. So that goes up way high. So 48 is going to be very close to 50. Right, oh, that wasn't on the line. Right over here. And then the last one was 96, so that's way up here near 100. A little bit past halfway again. Okay, so you can see it didn't feel like a lot was happening here at the beginning, and then all of a sudden it starts growing really, really fast. Okay, and again, as best you can, I struggle with this too. I'm going to try to draw my smooth curve connecting these, connecting those points. There, that's better. So you can see one difference between this and our previous graph is our previous graph was decreasing. It was going down to the right. Whereas this graph is increasing as we go to the right because it's getting larger and larger amounts of bacteria cells. But you can also see what they have in common is that just like how this one had that curve to it and was not just a straight line, that's also the case for this graph because what we're changing by each time is not a consistent amount, right? We're not adding the same amount each time here, right? This only added 3. Look at the difference from 48 to 96. That's much larger. So you're growing faster and faster and faster and faster the further you go through the function. Okay, so now we're going to write an explicit rule. We wrote the recursive, now we're doing explicit. Again, I would assume they want the a sub 0 one because that's what we start with in our table. and they want us to use special letters. So B is the number of bacteria cells, H is number of hours. So we're going to say the number of bacteria cells based on the number of hours equals our initial amount, which was 3 bacteria. And then every time we went to the next one, we just kept multiplying by 2 over and over and over again. And sometimes it helps me to kind of think of it as like we took the previous one, which was a 3 times 2, and we added this new times 2, right? And then this one, we took the previous one, which was in reality a 3 times 2 times 2, and we add yet another times 2, right? And when we write times 2 over and over and over again, we get tired of actually doing that. I'll just show you one more, just to show you how tired you'll get of this. Right? So it would be like a 3, and then we already had 3 2's. We add a 4th times 2. 2. And again, we've learned how to do this in a more efficient way. Instead of saying 3 times 2 times 2, I can just write 3 times 2 squared. And instead of saying 3 times 2 times 2 times 2, I can write 3 times 2 cubed. And then it would just continue that pattern from there. And that's why we use exponents to represent this repeated addition. Sorry, I got a little sidetracked there. All right, so yeah, 2 is what we're multiplying by over and over again. Because we started at 0, it's simply raised to the n. If you started at 1, it would just be raised to the n minus 1. No big deal. But we like when it starts at 0, because that's a lot easier. All right, so find the number of bacteria cells. They gave us the number of hours they want. They want 7 hours. So that would be 3 times 2 to the 7th power. Again, you have to type this all in at once in your calculator, or use order of operations. This has to be done first, and this is last if you do them separate. I find it easier just type it all in. And you should get a pretty big number here of 384 bacteria. Or bacterium. I don't know what the plural is. We're going to go with that. But yeah, so again, if you're not getting this number, please let a teacher know so they can help you out with that step with your calculator. Okay, so at this point in the video, why don't you give it a pause and see if you can figure out these recursive patterns that are geometric, so they're multiplying. So for this first one, the numbers get huge because what we're actually multiplying by is 6, which is pretty big common ratio. And for the recursive for that one, we're going to say the first term, because remember, a sequence always starts with a sub 1, equals 5. And to get the next term, we simply multiply by 6. I'm going to put times 6. All right, for the next one, you hopefully saw that not only were we multiplying by 3, but the sign is going negative, positive, negative, positive. And the only way that happens is if we multiply by a negative number. So those are pretty tricky. So it's a negative 3 that we're multiplying by. So you should have these negative 162, 486, and then negative 1458 as the next 3 numbers. So our recursive pattern would state the first term is a negative 2. And to get our next term, we're multiplying, and you need to put parentheses around it if it's got a negative, because when you write this, what is that? That looks weird. I don't know what that means. So please put parentheses around it. And I know the last one was scary, but with fractions, you just multiply straight across. So since the top, it wasn't changing at all, that means we were multiplying by something with a 1 on top. And if you look in the denominators, you can see that they're multiplying simply 2, 4, 8, so that's times a 2. So we're really just multiplying by a half for this one. And you can think of it as 9 over 1 right there if you want to, but that's all it is. So the numerator is simply staying the same, and the denominator is doubling each time. Okay, so we'll say the first term was a 9, And to get the next term, we multiplied by 1/2. Again, I like to use parentheses for fractions as well. So each of these problems involves a geometric sequence. How would you describe the difference between a geometric sequence and an arithmetic sequence? Okay, so today we've been working with geometric sequences, so let's think about that. So geometric, we would maybe say that this means you would have a multiplying pattern, and we call that number that you're multiplying by the common ratio. And it creates a curved graph. Okay? It can still go up or down. That part is not unique to either, but it creates a curved graph. So then if we think back to what we've been doing with arithmetic sequences, right? Those are adding patterns. And you can say subtraction too, but that's just adding a negative. So I just say adding pattern. We call their number a common difference. And it creates a straight graph. I don't know, straight line. Okay. And then the last thing we could probably compare is when we write the explicits over here, it's that, how would we say this? It's that term, the a sub 0 plus the difference times n. I know that looks scary, but that's what we've been doing. And today, with the explicit, it was the first term times that number we multiply by, which is the ratio, raised to the power of n. So basically, one of them is linear looking, mx plus b, and this one, it has another word we'll get to soon called exponential. And that concludes your video notes for geometric sequences.